Okay, last week was all about reminding ourselves how equilibrium problems work and then exploring some thermodynamic coupling to equilibrium, like what are the actual thermodynamic implications of having a chemical equilibrium. This week is all about attacking equilibrium from the standpoint of non ideality, from the standpoint of activities, and what we have to do to incorporate the effect of non-ideality into our equilibrium calculations. So we're all up on what an ice table looks like and how we can use it to calculate important quantities. What happens when those concentrations in the ice tables do not represent the actual chemical behavior, right? So to focus in on what we're going to be doing, we're going to be looking at aqueous systems. So we're going to be looking at things like solubility and acid-base behavior. And it turns out that one of the things that we assume with a Henry's law standard, which applies to dilute solutions, is that the particles in these aqueous systems, right, that result from dissociations. So acids dissociate into H3O plus and a counter ion. For solubility, you get pluses and minuses from the dissolution of a salt, right? These pluses and minuses, with the Henry's law standard, what we pretend is that these pluses and minuses do not interact. The standard where we build our equilibrium expressions, the standard that you've been using in your ice table calculations for these systems, is that they're dilute enough that the concentration, and using just the concentrations, that's fine, right? And that's enough to get the actual chemical behavior. The important thing to note, though, is we know that pluses and minuses, they do interact, right? So by Henry's law standard, just use the concentration because we can pretend that they're so dilute that they never ever really bump into each other. So we might as well pretend that they don't interact with each other. Everything's just a free-flowing ion. But we know that's not the case. So when it's not the case, what we'll have to do is those concentrations, they're not going to be fine. If we're away from this dilute limit, we know that we have to replace our concentrations with activities. So before we see the math associated with that sort of process, let's understand physically what we're saying about dilute solutions, interacting particles, and non-interacting particles, right? We're not talking about molecular interactions. What we're really focusing in on, when I say don't interact, you'll see what I mean. It's not that there is no molecular interactions there. It's just that the pluses and minuses don't find each other. So we're going to focus on the results. We're going to focus on the products of a dissociation. The pluses and minuses that are made. And I'm going to emphasize this whole non-interacting point again and again, right? So the easiest thing to do is to go ahead and look at water. And we know that water can dissociate by itself into H3O plus and OH minus. Now, associated with this equilibrium problem, okay, is an ice table. Okay. We see that Q equals 0 because there's zeros over here initially. Q then is less than K. We're going to get movement towards this side. The equilibrium constant that describes this is Kw, which is 1.0 times 10 to the minus 14. And then we know that we can solve this, and we get that X is 1.0 times 10 to the minus 7th, right? That means that we can set the pH scale based off of this number right here. The H3O plus concentration in water is 1.0 times 10 to the minus 7 molar. Same thing for the OH minus concentration, okay? This is producing dilute ions. This is 1.0 times 10 to the minus 7. It's really small, right? So in this case, because it's dilute, this is perfectly fine. This X can be viewed definitely as a concentration. When I bring my information down to my equilibrium expression, right, I'm left with something where I'm confident that what I'm getting out, okay, is something that I can analyze and describes the actual chemical behavior. Right? So what's the picture? Why is this okay? Well, here's water, right? Most of the molecules are H2O. Most of the H2Os are bumping into other H2Os. Now we know that, all right, the activity of this H2O is 1. So it's not going to really affect the equilibrium, right, because it's in a pure liquid state. Now, a very small number of these H3Os turn into H3O pluses. And a very small number of these H2Os turn into OH minuses. But the majority, all right, of the interactions are water-to-water interactions. Okay. What we focus in on are those solute interactions. Sorry, the solute interactions. Yeah, we focus in on the pluses and the minuses. And what we say when we think about activity is how likely are these guys to feel each other? Okay? So when I said no interactions before, it's about the pluses and minuses and how likely they are to find each other, right? Now, for dilute situations, this guy is going to be surrounded by water. It'll be floating around, right? There's only 1.0 times 10 to the minus 7 molar of this. There's only 1.0 times 10 to the minus 7 molar of this. It's very unlikely for these guys to ever bump into each other. So our assumption in our equilibrium expression that you get a set of H3O plus that are all floating away from a set of OH minus that are all floating away, not interacting with each other, just interacting with other waters, just being in that aqueous state, that's a pretty good assumption. So, as a counterexample, what happens when I take water, okay, and then I actually put a salt in it? So let's say I have KCl off to the side here, and KCl is a solid. Now we're going to analyze this like we did in general chemistry, and we're going to see that this analysis is incorrect, right? This analysis that we're just going to do right now. If I dump this KCl inside here, right, what you'll also get are K pluses and Cl minuses floating around, right? Now, what if I make this water solution, say, let me look at my example. Let's say I make this water solution 0.050 molar KCl. This is no longer really dilute. We throw this in here, and what would we say in general chemistry? Well, K plus and Cl minus, are they really going to have an effect on the chemical behavior inside here? From a general chemistry perspective, we say, well, K plus is the conjugate of KOH. That's where it comes from. So it's the conjugate of a strong species. So if it's a conjugate of a strong species, it's kind of like a spectator ion. Cl minus comes from HCl, which is a strong species again. Cl minus then doesn't have any acid-base properties. So sure, dump in as much KCl as you want. Water's still going to look like neutral water. The pH isn't really going to change. Nothing's going to affect anything. And from a general chemistry perspective, we still expect to get a pH of 7.0. But here's the thing. What we have to think about now is we put a whole bunch more of pluses and minuses into that scenario now. How likely is it for H3O plus, if there's this much ion floating around, how likely is it for it now to interact with a negative ion? It's probably not going to interact with OH minus, but could it interact and feel the Cl minus that's floating around? Absolutely. All right. Same thing for OH minus. Has its chemical behavior changed? Does it really feel like a whole bunch of OH minuses floating by themselves, surrounded by waters? If it feels these K pluses, well, no, its chemical behavior is affected by the presence of these ions, all right? It's no longer a dilute situation, right? We can't just assume that these ions are floating by themselves without ever feeling a Coulombic interaction with an oppositely charged ion. So concentrations in this case do not describe the whole chemical behavior because it's not dilute enough. So in Gen Chem, we would say no acid-base properties for this salt, so we would expect a pH of 7, and that's not actually the case. Right? And so we need to know how to deal with this and how to approach this from a mathematical standpoint. Right? Before we get there, and I'm going to do this example, and we're actually going to calculate the pH of this, which we would assume is 7. It's going to be close to 7, but we're actually going to see that it changes because the pluses and minuses interact, and so then we need to deal with activities. Okay. One other picture before we get there. Right. Remember what this is all about. All right, and I'm just going to kind of draw it in a big beaker. All right. This is about an equilibrium. And I'm just going to not use H3O plus. I'm going to use H plus. Remember, H3O plus and H plus, those are synonyms for each other. They mean the same thing, right? H plus and H3O plus, hydrated H plus, hydrated proton, hydronium, all the same. So this is the equilibrium that has to occur, right, inside this water. And in pure water, this is fine. And again, we can assume that these guys are floating around each other. They bump into each other rarely and they go back to make water, but most of the system is in this pure liquid water state. Well, if you think about it, to go back to this position right here, to go back to water, all right, they do have to bump into each other every now and then. It doesn't happen often, right? 1.0 times 10 to the minus 7, 1.0 times 10 to the minus 7. But now if I put something in the way, if I put a K plus in the way, or a Cl minus in the way, right? How often are they going to find each other, right? They find each other very rarely anyway because there's very few of them in there, right? H pluses and OH minuses. But now this is definitely going to affect how much they bump into each other, right? Ions are said to have this ionic atmosphere, okay? Think about it as like a region of influence around each one of the ions. So for this equilibrium to not be affected by the presence of ions in solution, for this equilibrium to be able to be looked at as just producing free-flowing ions, there's nothing that has to sort of interfere with those ionic atmospheres. But as soon as I put a K plus in there, and as soon as I put a Cl minus, as soon as I put any other ions in there, okay, this, which looks like it has an ionic atmosphere that's purely negative, now interacts with this positive. And so you're changing that ionic behavior. It's almost like a shielding kind of thing, you can think about it, right? It's not like this is going to be pure negative relative to this H plus anymore. Why is that? Because sometimes there's K pluses in the way. It's almost like you're decreasing its negative. And you can make the same arguments here. This has a certain ionic atmosphere, but what's it going to draw into its ionic atmosphere? It's going to draw the Cl minuses close. Remember, there's waters in the way. Remember, it's still mostly water. But just because there's water there doesn't mean that these interactions aren't going on. Okay? Even if there's water molecules in the way, this ionic atmosphere is going to be affected by the presence of Cl minus. So it doesn't look like it's quite as positive, right, as you would expect. Okay? So then when I put KCl in there, what's the effect on the equilibrium? Let's make a prediction. Okay? Do we expect more H plus to be floating in there now that K plus and Cl minus are there? Or less H plus to be floating in there now that K plus and Cl minus are in there? All right? And it ends up being the case that there's more H plus floating in this solution than there would be in pure water. Well, why? Because the ionic atmosphere of this is lessened. The ionic atmosphere of this is lessened. So these guys, which still have to bump into each other to go back and make water, these guys bump into each other less often, right? They bump into each other less often. So you actually get more H plus floating in solution when there are other ions in solution because they get in the way of these guys recombining and making water, right? The chemical behavior has changed, right? And because the chemical behavior has changed, the chemical activity is really what dictates how this equilibrium progresses. And so we shouldn't use, in this non-dilute solution, we shouldn't use just concentrations. We should actually amend our equilibrium problems to include activities. So then how would we approach this mathematically? Just always think about things can get in the way. And for like super concentrated solutions, even without like a K plus and a Cl here, we'll talk about acids that are really, really concentrated in a bit. These ions can get in the way of themselves. And they can shield themselves and they can affect their ionic atmospheres. And they can prevent even themselves from coming back together to forming the left-hand side. And we see that a lot with solubility, actually. So what do we do mathematically? Right. What we're going to need is something called the ionic strength. Let me get a different marker. So from our last discussion, right, essentially what we have is a situation where the number of ions in solution affects the chemical behavior. Of solute particles. The H plus is hydrated, it's H plus aqueous. The OH minus is hydrated, it's OH minus aqueous. They're solute particles. The presence of ions affects their chemical behavior, right? So what we have to do to account for this is we define this ionic strength, right? And this ionic strength is a mathematical quantity that actually accounts for the number of ions in solution. Ionic strength is given the symbol I sub C. It has units, okay, that are equal to molarity. So really what it is almost like an effective concentration. It's like a concentration of ions that are in solution, right? It does account for ions with different charge though. So the chemical formula that we need to memorize is that IC looks like 1/2 the sum over I Z sub I squared C sub I. Z sub I is the charge of species I in solution. C sub I is the concentration of species I in solution. This gives the ionic strength. What you'll see from there is once we have an ionic strength and we're quantifying or we're accounting for the number of ions in solution, we can apply theory or experiment to take, all right, this I sub C and modify, all right, our equilibrium problems. The theory or experiment we connect gives a gamma. It gives an activity coefficient, right? So we're going to start to do problems now where we're going to see the I sub C will give me a gamma. Once I have a gamma, an activity coefficient, then I can account for the actual behavior of the ions in solution, right? We're going to discuss the Bi-Huckel theory eventually, which you actually saw a bit last semester, real briefly. And then we're going to always kind of have these tables that I'll reference, and I already sent you one, okay? And we can experimentally determine these gammas, but we'll see whenever we experimentally determine a gamma, it's always based on or organized by I sub C. Okay? So the easiest thing to do to kind of figure out what we do here with these sorts of problems is let's go back to this example we were talking about earlier. And let's calculate the pH of a 0.050 molar KCl aqueous solution. And again, we're going to do it on the junior level now. We're not going to just assume that we have a pH of 7. what we're going to run into is a situation here where we're going to have to know that this is concentrated enough of a solution to affect the chemical behavior of ions, right? So here's the step-by-step process with how we'll approach this problem. We always focus in on the equilibrium we care about. So we're after pH. The only thing that is directly affecting pH, not indirectly affecting it, but directly affecting pH is our water dissociation again. It's not like we have an acid with a Ka or a base with a Kb here. We literally just have Kw to work with. We write the exact same ice table. Ice tables still keep track of concentration. All right. So nothing's new here. When I get down to my Kw expression though, what I'm going to remind myself is that what I really do to make this Kw expression manifest as appropriate mathematics is I look at my H3O plus concentration at equilibrium, and then I look at my OH minus concentration at equilibrium. This is the standard setup. Now we modify this. So we get to this point and we say, hold on a second, there are too many ions in solution to assume that the ionic atmosphere of H3O plus and OH minus are not affected by the presence of other pluses and minuses. There are too many ions in solution to assume that this is dilute enough where concentrations will just be okay to use in this expression. So what we have to use here instead are activities. The activity of H3O plus at equilibrium is really needed here. And the activity, the A, these are A's, the activity of OH minus at equilibrium is really needed here. They're still going to be equal to Kw, but in this instance, concentrations are not appropriate to describe chemical behavior. Activities are. Okay. So then if we can use a table to get a gamma, which will be the case here, all right, then I know I can replace each one of these activities by a concentration times gamma, right? So we know from the last week's discussion that whenever we have an activity, we've set up the thermodynamics such that activity is defined as, or one way to kind of rearrange a definition for activity coefficient, right? Activity is gamma times concentration. Okay? We will be able to look on that table I sent you, and we'll see that we'll be able to calculate an I sub C, and an I sub C will give me this gamma. So what I'm going to do now is I'm going to take my Kw expression, and in each one of these spots, I'm going to make this substitution. All right? So my activity of H3O plus really looks like gamma of H3O plus times the concentration of H3O plus. And my activity of OH minus really looks like gamma of OH minus times my concentration of OH minus. So I'm just going to rearrange this a bit. It looks like my concentration of H3O plus, concentration of OH minus, times my gamma of H3O plus, and my gamma of OH minus. Now before, when we just considered, right, that concentrations were okay, our expression was this. Our expression for those dilute situations looks like your concentrations are all you need to describe the chemical behavior. It really looks like your gamma is equal to 1. When is gamma equal to 1? Under ideal conditions. What I'm saying here now is these gammas, we shouldn't assume they're 1 because I'm going to be able to look on a table, and with the ionic strength that we'll be able to calculate, we'll see that these gammas are different than 1. And if they're different than 1, they're going to affect the chemical behavior here. Our ice table gives us the concentration of H3O plus as X. My ice table still organizes concentration and gives me the concentration of OH minus as X. So my new expression that I have, again, just reinforcing these concepts over and over again, Kw doesn't just look like X squared, organized by my ice table. It's X squared, H3O plus, OH minus, those two gammas, those two activity coefficients. So let's talk about using your table. The table that I gave you in the announcements this week, right, involves finding gammas by I sub C. And what you'll see is you'll find H3O plus in that table, and you'll find OH minus in that table, right? And you'll see that these guys are grouped with different species at times, and it's all based off of size. The first column has like a picometer reading in it. That's just reminding you that these ionic atmospheres, they all have a different size. So these species are going to be affected differently by pluses and minuses there, okay? So you kind of get to ignore that column in terms of pulling information off of it, but it's important to realize that that physical argument still needs to be made. It's all about the size of the influence of the plus and the minus being affected by other pluses and minuses present, right? Let's calculate I sub C, right? There are 4 different ions in solution here, right? So let's just go ahead and write out what we mean symbolically first. There's K pluses floating around. There's Cl minuses floating around. There's H3O pluses floating around and OH minuses floating around, right? KCl aqueous, remember, is K plus and Cl minus. There's like a 1-to-1 stoichiometry there. So the concentration of K plus is 0.050 and the concentration of Cl minus is 0.050. Hopefully you can see that as a Gen Chem type recognition idea. What I'll need inside here is the charge of K plus, the concentration of K plus, and remember I sub C is a sum. I'm going to need the charge of Cl minus times the concentration of Cl minus. I'm going to need the charge of H3O plus times the concentration of H3O plus, and I'm going to need the charge of OH minus, right, times, the charge of OH minus times the concentration of OH minus. That's my sum. So that's how we interpret the I sub C notation. That's what it looks like from the standpoint of actually writing it out. Now, for these species, right, the concentration of H3O plus and OH minus, we know that those are small, right? We can kind of look at the gamma equals 1 situation and say, well, this is 1.0 times 10 to the minus 7, so is that. Even if these are affected, they're not going to be affected in a way where 0.050 is an appreciable sort of comparison to these small ideas here, these small quantities. So what we're going to do now is we're going to neglect these guys, right? We could put 1.0 times 10 to the minus 7 there as an estimate for that concentration, and 1.0 times 10 to the minus 7 there as an estimate of that concentration. But that's just going to be so small that we might as well get rid of them because they're added and they're small. Just get rid of them. So our IC is really based off of all of these K pluses and Cl minuses that are there. Those are the main things affecting the behavior, all right, of the ions in this solution. So our IC in this case looks like, well, oh yeah, and these charges are squared. Make sure you make that correction in your notes. Those charges are squared. So this looks like 1 squared times 0.050 molar. And this looks like negative 1 squared, which becomes positive 1, right? Concentration of Cl minus, 0.050 molar. So this is nice for these nice 1-to-1 salts. We call them 1-1 salts because they just produce 1 ion of each charge. Our IC is actually equal to 0.05 molar. So now what we can do is we can look on our chart. And what we can find is what's the activity coefficient for H plus, which is the same as the activity coefficient for H3O plus when IC is 0.050 molar, right? And when I look on that chart that I gave you, what I get is that this is 0.86. So is gamma 1 anymore? No. It actually is deviated from 1. So we actually expect to get a different X, a different concentration of H3O plus. What about OH minus? The gamma for OH minus is 0.81. These have different gammas because they have different sizes, different effects of all these ions floating around. But again, is this 1? Is that a good approximation? No, it's 0.81. So now, after looking on that table and pulling the correct values there, I can go ahead and I can solve for X. And I can see how the concentration of ions have changed now based off of considering the activity of those ions and not necessarily just their concentration. So I substituted my Kw, and I now have an X to solve for. When I solve for this X, right, and please check my math and let me know if you find a math error so I can send out a message to everybody. These are all new examples. So please make sure you can reproduce my work, all right? What I get here is, instead of getting 1.0 times 10 to the minus 7th out of my calculation, what I get for my X is 1.19814 times 10 to the minus 7, right? My H3O plus concentration in this instance is like 1.2 times 10 to the minus 7 molar. And all I did was put in a neutral salt. All I did is put in a salt that doesn't have any real acid-base properties. But what it does do is that salt affects the ionic atmosphere of H3O plus and OH minus. And what do I see? I see more H3O plus than I expected is actually in solution. Why does this make sense again? The H3O plus is prevented from finding OH minus and going back to water due to the K plus and the Cl minus floating around. There's like a screening effect that happens. It affects those ionic atmospheres. You actually get more H3O plus than you expect. So we know the pH of neutral water is 7. So what's the pH of this solution? An important note. In general chemistry, we lied about pH. All right. In general chemistry, we always write pH as the negative log of the concentration of H3O plus, which again, remind yourself, is also the negative log of the concentration of H plus, right? That's not actually the case. In actuality, the pH is the negative log of, you guessed it, the activity of H3O plus. A pH meter, a pH probe, doesn't directly measure concentration. It measures how often it can find an H3O plus, a free H3O plus. It actually measures how much it can find, right? The activity of H3O plus, its true chemical behavior. So if I want to calculate the activity here, right? And again, make sure that you can, or the pH based off the activity, which is the actual definition of pH. Again, make sure that you check my math. What I do here is I'm going to take my unrounded X from above, okay? Because that on my ice table is my H3O plus concentration. I'm going to use the unrounded version down here. I'm just going to write it as X. And then I'm going to take my gamma of H3O plus and include it in there as well. Why is that? Because remember, the definition of activity is concentration, right, at equilibrium, concentration times my gamma, and what I care about for pH is the concentration at equilibrium. So X was my concentration, gamma is my gamma. I go ahead and get my pH here. So just by putting in salt, what I get when I do this math is I get a pH of 6.99. So this is why we tell you in general chemistry, all right, that yeah, you put in KCl and it doesn't really change the pH. It's just like this salt that doesn't have any acid-base properties. So you get a pH of 7. But do we actually get a pH of 7? No. And what do we see? We actually see that the pH has gone down a bit. Okay? And so if the pH has gone down a bit, right, it's actually a little bit more acidic than what we thought of before. The activity of H3O+, right? It actually feels like we have a little bit more chemical activity of H3O+ than in neutral water, and all we did was put in a salt. A salt that doesn't itself have any acid-base properties, okay? So this is really interesting, all right? You might be saying, well, this is really close to 7. Why go through all this? Remember that eventually, right, chemists care about trace amounts of stuff. When we're doing environmental chemistry, biochemistry, small amounts sometimes affect drastically the chemical behavior of those systems. So you might be saying 6.99, that's not really a big deal, right? But it might be, right? Depending on the situation, depending on the actual application, okay? 1.2 times 10 to minus 7 compared to 1.0 times 10 to minus 7 doesn't seem like a big deal, but what if it's actually accounting for some sort of pollutant or something that's going to affect your physiology in a certain way? That's why understanding the behavior of activity instead of simply concentration from the standpoint of calculations is going to be important for us. So try to comprehend as much as you can, follow these ideas, be able to make the physical arguments as well, all right? And what we're going to do is we're going to reinforce these concepts over and over again with the subsequent videos.